How much can we mess up the real line? By the real line, I mean the real numbers equipped with their natural order. One feature it has is that it contains arithmetic progressions. In fact, they appear absolutely everywhere. You could pick any point you please, jump in either direction by some fixed amount, and never run into any issues. In 1980, Paul Erdős and Ronald asked a puzzling question. Would it be possible to reshuffle the real line to get rid of arithmetic progressions with k terms? Better yet, could we get rid of progressions containing only 3 terms? Rather marvelously, the answer is yes. Hayri Ardal, Tom Brown and Veselin Jungić proved this in their 2011 paper titled Chaotic Orderings of the Rationals and Reals. And in this video, I'm going to show you how they did it. To make things clear, I'll make precise what I mean by reshuffle. The standard order on the real line is a binary relation with 3 properties. It is connected, meaning for any distinct A and B, either A comes before B or B comes before A. It is transitive, meaning if A precedes B and B precedes C, then A should precede C. And it is irreflexive, a number never precedes itself. A new order then is simply a connected, transitive, irreflexive binary relation on the reals, which might give different answers on what comes before what. For instance, whilst 1 usually precedes 2, perhaps the new order sees 2 as coming before 1. So the presence of a 3-term arithmetic progression in this sense would be 3 reals ABC all in decreasing or increasing order inside the shuffled line, where the difference between A and B is equal to the difference between B and C. They call an order chaotic if it prevents this from ever happening. The authors start with the much simpler case of the integers. To create a chaotic order, they isolate the pair -1 and 0, and dictate that 0 should precede -1. They then copy and paste this expression, putting one before the other, and then convert the left block into even numbers by multiplying all terms by 2, and convert the right block into odd numbers by multiplying terms by 2 and adding 1. Then simply have the first block precede the second. This now gives the integers between -2 and 1 devoid of arithmetic progressions. To continue, simply repeat the same process. Copy and paste what you currently have, convert one piece to evens and the other to odds, and place the even before the odds. This never contains arithmetic progressions because either all terms are of the same parity, placing them in the previous block, which by induction does not contain such progressions, or the terms switch parity twice, which isn't possible in this ordering. Then, since any pair of integers eventually appears in this process and their order is preserved in future steps, this generates a well-defined chaotic ordering of the integers. Quite clever. Next step, the rational numbers. Well, given any finite set of rationals, we can certainly order them chaotically. You could put them all on the same denominator, look at the numerators, shuffle them according to the chaotic ordering on the integers, which gives you the original rationals now free of arithmetic progressions. Unfortunately, this doesn't define a suitable ordering on the rationals. Even if we agree on taking least common denominators and so on, this relation is not transitive. The authors cleverly remedy this issue by creating a tree. A mathematical tree is simply a connected graph that doesn't contain any cycles, meaning closed loops. The boundaries of the edges are usually called vertices. To create this special tree, they start by enumerating the rational numbers. This is possible because the rationals are countable, but there are lots of fun explicit enumerations as well. The point is, it can be done. So fix an enumeration and take the very first rational in the list. We'll stick it at the root of our tree. Next, take the first and second in the list and put both possible orderings of that pair on the second level of this tree. Next, take the first 3 rationals and have each vertex on that level represent every possible chaotic ordering of those 3 rationals. We continue in the same vein. On level 4, vertices will represent all possible chaotic orders of the first 4 rationals, and so on. Crucially, by our previous result, there is always at least one chaotic ordering of the first n rationals, so this process never halts. Whilst not every vertex has an extension on the level above, every vertex on some level contains a suborder represented by a vertex below it, and that is precisely how we create this tree. We simply join vertices with those at the next level up which contain that ordering. Now comes a really nice move, a famous result in graph theory called Konigslever. A special case of this says that an infinite tree where every vertex has finitely many neighbors must contain an infinite branch, meaning an infinite path. What does this mean for our tree? Well, it's saying, yes, there is a chaotic ordering of the rationals, and it's represented by this infinite branch. And finally, we come to the reals. To deal with the reals, we need more machinery. The authors use a Hamel basis. A Hamel basis is a set of real numbers with the following special property. Any non-zero number x can be written uniquely as a finite linear combination of elements from the Hamel basis with non-zero rational coefficients. It isn't possible to explicitly write down a Hamel basis, but its existence is offered by something called the axiom of choice. Of course, whilst this linear combination is unique to each real, there is nothing preventing us from adding on other basis elements but sticking a zero in front of them. This is actually a good idea for what follows. Let's finally define this order we're after. Take any two distinct numbers a and b and represent them as a linear combination of Hamel basis elements. Now, on one end we have the basis elements used for a, and on the other we have the basis elements used for b, and perhaps some of these are in common with a. But to properly compare a and b, it's a good idea to take the union of both of these sets and write a and b in terms of that resulting set of basis elements. To keep things organized, let's also insist on writing them in ascending order, using the standard ordering of the reals. Remember that some of these a and b coefficients may now be zero. Writing a and b in this way allows us to compare coefficients. The idea is to do this from left to right, and stop as soon as we find a pair of distinct coefficients. So perhaps a0 and b0 are the same, but let's suppose that a1 and b1 is the first instance of differing coefficients. Now, these are rational numbers, and we have a chaotic ordering on the rationals. So let's suppose that a1 precedes b1. We will then simply stipulate that the real numbers a and b inherit the same order. Similarly, if b1 preceded a1, we would define b as preceding a. And this defines an ordering on the reals. Clearly it is irreflexive and connected. Take a moment to appreciate why it is transitive as well. But the question is it chaotic? Let's find out by taking three numbers a, b, c. As previously, let's represent these using the union of the Hamel basis elements which would come into a, b, and c. What would it mean for these to be an arithmetic progression? We'd need something like the difference between a and b and c to be the same, as well as a preceding b preceding c. So let's look at the two sides of the yellow expression, but in terms of this basis. As before, we can now compare coefficients, which need to match up if both of these things are the same by uniqueness. Take the first coefficient pair telling us that b0 minus a0 equals c0 minus b0. Now, notice that if any of these three are the same, in other words, if a0 equals b0, or c0 equals b0, or c0 equals a0, then automatically the right-hand expression is equal to 0, meaning a0, b0, and c0 are all equal. So let's just suppose that this is indeed the case for this first coefficient pair, and let's look at the next one. This time, let's see what would happen if a1, b1, c1 were all distinct rational numbers. Now, because a precedes b, by our definition of this ordering on the reals, a1 must precede b1, and because b precedes c, b1 must precede c1. But these are rational numbers, and our order on the rationals is chaotic, which forbids this from happening. So it cannot be that a1, b1, and c1 are all distinct. The same reasoning applies to all the coefficient pairs, meaning both of these expressions are in fact 0. Which then contradicts that a, b, and c are in increasing order according to this ordering. So, in conclusion, the statements that the differences are equal and that they are in the hoped order are incompatible, and thus the ordering is indeed chaotic. I hope you enjoyed this video, and I would encourage you to read the fully fledged proof written by these three mathematicians, as it is really wonderful work.